Now, there's one other thing I just want to mention. I said that when you have your two aircraft traveling in different directions, not only do they become foreshortened in space, but they become foreshortened in that dimension too, which of course in our previous thing was time. So that means that if this is time and that is space, that when they change the direction, that means that the rear of the plane is going to go ahead in time and the front of the plane is going to go behind in time. And so that seems kind of weird, but it's not weird at all. Let's just take a quick look at how that actually works. Let's start out with a 1 kilometer long train on a train track. I'm just going to draw it boxy here because I don't want to take the time to be clean about it. And he's on a train track. And he's 1 kilometer long. It's a slow train, slow freight train, traveling at 1 kilometer per hour. Now it comes to a station. Let's put the station right here. If the front of the train reaches the station at noon, traveling at 1 kilometer per hour, a kilometer long train, when is the rear of the train going to reach the station? It's going to reach it at 1 o'clock. It's going to take an hour for the whole train to go through the station. Now let's length contract that train. So there's our 1 kilometer long train, and we're going to length contract it to, let's just make it half the length. That look like half the length? Close enough. So it's 1/2 kilometer. And we're going to center them on the same point. So now we have the 1 kilometer long train and the 1/2 kilometer long train, and they're both traveling at 1 kilometer per hour. Now we come and the long train has just hit the station at noon. How about the front of the shorter train? Oh, it's behind, not only in space, but in time. It's going to arrive late. So traveling at 1 kilometer per hour, 1/2 kilometer long, it's going to be a 1/4 kilometer. It's going to arrive at the station at 12:15. So the front of the train, simply by being length contracted, falls behind by 15 minutes. So it's not really as spooky as it may sound. By length contracting, we also bring the front back in time and the rear ahead in time, but it sounds kind of weird, but it's really not weird at all. It's just something shorter. All things considered, it's going to be taking different points in time. And so the middle of the train is going to come and hit the station at 12:30. And how about the rear of the short train? It's going to hit the station at 12:45 because it's going to get there sooner than the rear of the long train. And the rear of the long train finally reaches there at 1 o'clock. So we do get a foreshortening in time as something moves in space, but that foreshortening in time is not nearly as weird as we might think. Yes, the front of the train is behind in time. It just means it's going to arrive later. Yes, the rear of the train is ahead in time. It just means it's going to arrive earlier because it's shorter. So no big deal there, not nearly as spooky as some of the other things in special relativity. So anyway, I hope that I've taken the scary math of the Lorentz transformation. There's our gamma is equal to 1 over the square root of 1 minus velocity squared over speed of light squared. And alpha, which is very useful, is going to be just the reciprocal of that. And I've shown that these are just simply rearrangements of the Pythagorean theorem, especially alpha. That's the easiest one to see. And I do have a video where I show that rearrangement. And so that implies, which I actually demonstrated, that this can be plotted out in Euclidean geometry and vector analysis to show how length contraction and time dilation must occur if time is a fourth dimension with the same properties as the 3 dimensions of space. Because, once again, here's our airplanes traveling in different directions. Each plane is going to see the other plane falling behind in space. Each plane is going to see the other plane foreshortened in the direction that it is going, and also foreshortened in the direction perpendicular to the direction it's going. So we get that foreshortening. But if this is now time, and this is space. And by putting our planes together, not moving, they're not moving through space, but they are moving through time, then we move one of the planes that's moving through both space and time. It must trade some of the velocity through time for velocity in space, therefore it falls behind in time, and must also be length contracted, because now the space here is going to be somewhat, 100 meters is now going to be foreshortened to 70.7 meters, but not quite as easy as in the original scenario where we're working strictly in space. We now have an actual measurement. I measure this object, it's going to be shorter in space. So moving through space does foreshorten things. So that movement causes it to fall behind in time and causes it to foreshorten in space, or length contraction. And then we showed that if we're traveling in space and time, we must take into account that length contraction. So if something travels through space, it actually travels less distance the faster it goes. How weird is that? But yeah, if we are going through space, we feel stationary and space appears to be traveling through us. Therefore, space itself is foreshortened or length contracted. Therefore, distances are less in the direction we are going. So as I showed, 90 million kilometers at 70.7% of the speed of light becomes only 63,600,000 kilometers. And so the object traveling through space actually goes a shorter distance to get to the same distance. So the not moving observer sees something 90 million kilometers away. Someone goes there at 70.7% of the speed of light and finds out it's only 63,600,000 kilometers away. And since they're still traveling at the speed of time through time, their clock takes less time. Instead of taking 10 minutes, it takes 3.53 minutes. It takes less time to get there because traveling at the same speed, shorter distance, less time. So their clock ticks off less time. And when they come back, clock's still ticking off less time because it's a shorter distance. And we find that when they come back together, that the observer who's stationary sees them go out and back and sees it take 10 minutes. But he looks at the moving observer's clock and it's only ticked off 7.07 minutes. So that's because he simply went through less space. So to solve all these things visually, we do have to take into account time dilation and length contraction. And when we put them together, we find that everything works out. We find that there is no twins paradox because, of course, the clocks disagree because due to length contraction, he went through less space than the other one saw him go through. Kind of deep thinking here, but if you draw these vectors and play around with it as much as I have, it becomes obvious that length contraction and time dilation must occur. So I've pretty much wrapped my mind around special relativity in such a way that I'm very comfortable with it. Now I need to make the next step, which is to conquer general relativity, which Einstein talks about later in his book because he uses special relativity to show how general relativity must occur. And I'm not there yet, but I will be telling you when I've made that journey. So I hope you found this useful and informative. And if you did, please give me a thumbs up below. It's going to help other people find these videos and help people find the channel. And if you want to help me continue to put these videos up and to continue teaching you about relativity, you can go to patreon.com/Vocademy and pledge your support. Or you can go to support.vocademy.net and find other ways that you can help me make these videos and help keep Vocademy free. And you can take my course in relativity at vocademy.net. So a big thank you to my patrons and my other sponsors. I could not make these videos without your support, and thanks to everyone for watching.